Alright guys, today is Friday, it is September 24th, and I hope that you guys just did really well on your limits quiz. Looking forward to grading them on Monday. In the meantime, we are going to proceed and start talking about some of the sections in 2.4, rates of change and tangent lines. Your homework tonight is going to be what was supposed to be last night's homework. That's on page 92, 2, 4, 6, 7, and 8. Okay, so let's get started with a warm-up. What is the equation to find the slope of a line? And hopefully you guys can tell me automatically that the slope m is equal to y2 minus y1 over x2 minus x1. It's just your general formula to find the slope of a line between 2 points. What does it represent? Hopefully by now you're thinking that it represents something like rise over run, or basically just like a rate of change. How much this top thing is changing based on how much time you're giving it. So we can talk about feet per second as a rate of change, which is really just a slope. And we will be talking about tons and tons of different things and what they mean as rates of change. Today's lesson is going to be really quick. We are going to focus in on one of these two things. Since the slope of a line is constant, as you guys can read, you can pick any 2 points on the line and use the formula for slope to get the slope for the whole line. And that's really handy because it's a line, and that's easy to do. However, on a curve, the slope is constantly changing. Even if you just imagine the curve y equals x squared. When we look at this curve y equals x squared, all the way down here, the rate of change or the slope of this curve is changing over time, right? Over here, it's pretty quickly changing, and it's a negative rate of change. It's a negative slope. As we get towards the bottom, the vertex here, the slope gets towards 0. And as we move away, the slope starts getting steeper and steeper and steeper again. So we can think about these rates of change or this slope in two different ways. We can think of it as an average rate of change, right, which is what we're going to actually talk about today. And it's when we pick randomly 2 points on a curve and find the slope of the line between them. And this will be an approximation for the rate of change for the whole function between these two values. And we can also think about instantaneous rates of change. And that is a rate of change or the slope at a specific point on the graph. Which is more like what we're used to with a line, but how fast is the function changing at this one specific point? This would be instantaneous. So calculus is a huge study of instantaneous rate of change, and before we actually start that, we're going to focus on average rate of change, and later on we're going to use that to predict, or we're going to do it right now, the instantaneous rate of change for a function. Okay, average rate of change has a lot to do with something called secant lines. A secant line, you may remember them from when you learned about circles in geometry. A secant line is when you pick 2 points and you connect them with a line. So it's a line that has 2 points on the curve. And here we have in diagram 1 a picture of a secant line going from P to Q. The slope of this secant line will be the average rate of change. So the slope of the secant is the same thing as the average rate of change between these two values, P and Q. The other alternative, that second thing I was talking about, was the instantaneous rate of change, and that's the slope at one specific point, how fast it's moving. And that is actually called the slope of the tangent line. Instantaneous rate of change goes with slope of the tangent line. And last but not least, you can see on this third picture over here that what's kind of cool is that if you keep drawing secant lines, if this is PQ and then you move Q a little bit closer and it comes right here, and then we move Q even closer and it comes right here, and as we keep moving Q closer and closer and closer, what's pretty cool is that these secant lines begin to look just like this tangent line. And that's kind of the goal with calculus is how to use this idea of a secant line to actually come up with an equation for a tangent line or a tangent slope. Okay, like I said, today we are going to use this equation to find the slope of a function, or basically not the slope, the secant slope. I should actually addend that. Secant slope of a function on a specific interval. And it's kind of exactly what you would think of based on the equation for the slope of a line, where basically it's their y values, y2, right? This is really just y2 minus y1 over x2 minus x1. So we just write that as f of b minus f of a over b minus a. And this will find the slope of the secant line on this interval from a to b. Okay. I'm guessing you guys probably care the most about an actual example, so let me do an example for you. So here we have, we're going to want to find the slope of the secant line, which is the average rate of change of the following functions on these given intervals. So here's my first function, f of x equals x squared minus 2x. So for the slope, we're going to want f of b minus f of a over b minus a. Doesn't really matter which one's a and b. Let's go ahead. We'll choose them. So this one's going to be f of b. So when I plug 3 into this equation, I'm going to have 3 squared minus 2 times 3. That's f of b. Minus f of a, negative 1 squared minus 2 times negative 1 all over b, that's 3, minus a, negative 1. Okay, let's just simplify this. 3 squared is 9. 9 minus 2 times 3, 9 minus 6 is 3, I believe. Minus, let's look in here, we've got 1 minus 2 times negative 1, so that becomes plus 2. So this is 3 minus 3 over 3 minus negative 1. 3 minus negative 1 is 4. So to me, this looks to be 3 minus 3, which is 0 over 4. So according to this, the slope of the secant line from negative 1 to 3 is going to be 0 here. Okay, next problem. We're going to want f of b, or basically now we're talking g of b minus g of a over b minus a. Let's plug in these values. First, I'm going to plug in b. So g of b will be 1 over 5 plus 5, 1/10, minus, I'm going to plug in a, 1 over 0 plus 5, which is 1/5, all over b minus a, 5 minus 0. So that's just 5. 1/10 minus 1/5, we need to be able to add these fractions. Common denominator is going to be 10, so I have to multiply this one by 2 over 2. This will be 1 minus 2, which will be negative 1, over 10, because they have that common denominator, divided by 5. See why we did what we did with the limits. Negative 1 over 10 times 1 over 5, because it's multiplying by the reciprocal, that's negative 1/50. So these are all the slopes of the secant lines on these intervals. Let's do the last one, h of x. We're going to do h of b minus h of a over b minus a. If I plug in 2, I get the square root of 6 times 2, which is 12. 12 minus 3 is 9. So root 9 minus, if I plug in 1, I get 6 minus 3, which is 3. So root 3 all over b minus a, 2 minus 1, which is just 1. The only way I'm going to simplify this is root 9 is 3. 3 minus root 3 over 1. You don't even need the over 1. All right, guys. So that's all you're doing tonight for homework. The only additional thing you might be asked is you might be asked multiple secant lines, and then you might be asked to predict what the slope of the tangent is. And my suggested way of doing that is just to look at the pattern and see whether or not the secant lines are becoming closer and closer to a number as you get closer and closer to the value you're talking about. And if you're not sure what I mean by that, try your homework, and we'll discuss on Monday. Hope you have a good weekend.